The universe is older than we ever imagined. Good evening. There is something deeply humbling about looking up at the night sky. For thousands of years, humanity believed those tiny points of light were simply decorations, fixed jewels hanging from an unchanging ceiling. Our ancestors couldn't have imagined that every one of those lights was a sun, that countless others were too distant to see, or that the darkness between them was filled with galaxies, stretching farther than the mind can comfortably grasp. But perhaps the greatest surprise of all isn't how vast the universe is, it's how old it is. For much of human history, we assumed the cosmos had existed for only a few thousand years. Then science stretched that number into millions, later billions. Today, the age of the universe is estimated at approximately 13.8 billion years. That number is so enormous that it slips through our imagination like water through our fingers. We say 13.8 billion years as though we've understood something profound. But have we? Imagine compressing the entire history of the universe into a single calendar year. The Milky Way forms in early spring. Our sun appears only in late August. The dinosaurs don't arrive until Christmas Eve. They disappear on December 30. Every civilization you've ever heard of, every kingdom, every empire, every philosopher, every inventor, every work of art, every scientific revolution, every love story, every triumph and tragedy fits within the final seconds before midnight on December 31. There is something profoundly difficult about grasping the age of the universe because the numbers involved exist far beyond the scale of ordinary human experience. We understand seconds, hours, years, and perhaps even centuries because they fit comfortably within the boundaries of our lives and our history. 1,000 years feels ancient. 10,000 years reaches back beyond recorded civilization. 1,000,000 years seems almost unimaginable, yet the universe is approximately 13.8 billion years old, a span of time so immense that our minds struggle to give it genuine meaning. We can pronounce the number with ease, but understanding it requires an entirely different level of imagination. Every additional zero represents an enormous leap in duration, and billions of years stretch far beyond any intuitive sense of time we possess. To appreciate such immensity, imagine reducing the entire history of the universe to a single calendar year. The earliest moments occur in the first instant after midnight on January 1. As the months pass, the universe expands, cools, and gradually becomes a place where matter can gather into larger structures. Vast clouds of gas collapse under gravity to ignite the first stars, illuminating a cosmos that had previously been dark. Those stars live out their lives across what would correspond to many months on this compressed calendar, enriching space with heavier elements before new generations of stars emerge. Our own solar system does not appear until late August, meaning nearly 2/3 of the cosmic year has already passed before Earth even exists. Even after Earth forms, life does not appear immediately. Hundreds of millions of years pass before the simplest organisms begin transforming the planet. The oceans quietly host microscopic life for immense stretches of time before complex creatures evolve. Entire geological eras unfold at a pace that makes human history appear almost non-existent. Dinosaurs dominate the Earth for what would amount to several days on this cosmic calendar, yet even their reign occupies only a brief chapter compared to the universe's full history. Their disappearance occurs just before the final moments of the year, leaving room for mammals to flourish and eventually for human beings to emerge. The appearance of our own species occupies only the last few minutes before midnight on December 31. Agriculture, written language, mathematics, philosophy, architecture, literature, exploration, industry, electricity, flight, computers, and space travel all occur within the final seconds. Every civilization that has risen and fallen, every empire that once believed itself eternal, every scientific discovery that transformed our understanding of reality, every individual who has ever lived, loved, struggled, or dreamed exists within a tiny fraction of the closing moments. A single human lifetime would be shorter than the blink of an eye on this cosmic scale, an almost imperceptible instant within a history measured in billions of years. This perspective does not diminish humanity. Instead, it reshapes our understanding of significance. Our lives are undeniably brief, yet within that brief interval, we have developed the remarkable ability to reconstruct events that occurred billions of years before our existence. Through careful observation, mathematics, and experiment, we have traced the history of galaxies, measured the expansion of space, detected ancient light that has traveled across the cosmos for nearly the entire age of the universe, and pieced together a narrative that stretches back to the earliest moments after the cosmic beginning. The immensity of cosmic time challenges our intuition, replacing familiar scales with a history so vast that every moment of human existence becomes part of a far older and far grander unfolding reality. Human beings have always measured themselves against the world around them. We compare our height to mountains, our lifespans to ancient trees, and our achievements to those of previous generations. Yet no comparison is more transformative than placing ourselves within the timeline of the universe. The moment we do, our familiar sense of history begins to dissolve. The events that seem impossibly distant in human memory become astonishingly recent when viewed against the backdrop of cosmic time. The rise and fall of civilizations, the invention of writing, the construction of monuments, and the discoveries that reshaped our understanding of the world all occupy only the final moments of an unimaginably long story that began billions of years before our planet existed. Earth itself is not an ancient witness to the beginning of everything. It arrived remarkably late. For more than 9 billion years after the universe came into existence, there was no Earth, no sun, and no solar system. During those vast ages, gravity sculpted immense clouds of gas into galaxies, stars were born and extinguished, and countless generations of stellar evolution transformed the chemical composition of the cosmos. Entire chapters of cosmic history unfolded before the material that would eventually become our planet had even assembled. We often think of Earth as old because it has existed for about 4.5 billion years, yet in the chronology of the universe, it is the product of an already mature cosmos. Life appeared only after Earth had cooled and stabilized. Even then, it remained simple for billions of years. Single-celled organisms quietly inhabited the oceans while continents shifted, climates changed, and the planet evolved. Complex life emerged relatively late, and intelligent life arrived later still. If the history of the universe were compressed into a single day, modern humans would appear only in the final fraction of the final second. Everything we identify as civilization would occupy an interval so brief that it would almost disappear from view. The pyramids of Egypt, the libraries of antiquity, the Renaissance, the Industrial Revolution, the digital age, and every scientific breakthrough would be nearly indistinguishable on such a scale. This realization alters the way we think about ourselves. We are accustomed to placing humanity at the center of our stories because every human narrative begins with human experience. But the universe follows no such perspective. Its history was unfolding long before there were observers to witness it. Galaxies collided, stars ignited, and planets formed in complete silence, indifferent to whether anyone would ever exist to study them. We are participants who entered the story extraordinarily late, inheriting a universe that had already undergone billions of years of transformation before our arrival. Yet our lateness does not make our presence insignificant. It reveals something extraordinary about the progression of cosmic history. After billions of years governed by the interactions of matter, energy, gravity, and time, the universe produced conditions capable of supporting conscious beings who could reconstruct its past through evidence rather than memory. Every observation made through a telescope, every equation describing the evolution of stars, and every measurement of ancient light allows us to look backward across billions of years, reaching toward events that occurred unimaginably long before the first human mind existed to ask where it all began. At first glance, the stars appear to be little more than distant points of light scattered across the night sky. Their beauty has inspired myths, poetry, navigation, and wonder for thousands of years. Yet beneath that quiet glow lies one of the most extraordinary processes in the universe. Stars are not merely objects that illuminate the darkness. They are immense cosmic furnaces where the very ingredients of life are forged. Every heartbeat, every breath, every living cell owes its existence to events that unfolded inside stars billions of years before our planet formed. The connection between the human body and these distant suns is not poetic metaphor but physical reality, written into the atoms that compose every living thing. When the universe first emerged, it was astonishingly simple. In its earliest moments, only the lightest elements existed in significant amounts, primarily hydrogen and helium, with tiny traces of lithium. There was no carbon to build living organisms, no oxygen to fill the atmosphere, no calcium for bones, no iron for blood. The young universe possessed the raw ingredients for stars, but lacked nearly all the elements required for planets and life. It was a cosmos waiting for transformation, and that transformation began when gravity gathered enormous clouds of hydrogen gas until pressure and temperature at their centers became so intense that nuclear fusion ignited. Fusion is one of nature's most remarkable processes. Deep within a star's core, hydrogen atoms collide with such incredible force that they merge into helium, releasing vast amounts of energy in accordance with Einstein's famous relationship between mass and energy. This energy pushes outward while gravity pulls inward, creating a delicate balance that allows stars to shine steadily for millions or even billions of years. As stars exhaust their hydrogen fuel, the increasing pressure and temperature enable them to fuse heavier and heavier elements. Helium becomes carbon. Carbon combines to create oxygen. Successive stages of fusion produce neon, magnesium, silicon, sulfur, and eventually iron. Each stage represents another chapter in the gradual enrichment of the universe. Iron, however, marks a turning point. Unlike the fusion of lighter elements, creating elements heavier than iron no longer releases energy. For massive stars, this signals the beginning of a dramatic collapse. Gravity suddenly overwhelms the outward pressure that had sustained the star for millions of years. Within moments, the core implodes, triggering an explosion so powerful that it briefly outshines entire galaxies. These cataclysmic events, known as supernova, generate temperatures and pressures great enough to forge many of the elements heavier than iron, including gold, silver, uranium, and countless others that cannot be produced during the ordinary life of a star. The explosion does far more than create new elements. It hurls them across interstellar space at enormous speeds, mixing them into vast clouds of gas and dust. Over millions of years, these enriched clouds become the birthplace of new stars and planetary systems. Our own solar system formed from one such cloud approximately 4.6 billion years ago. The Earth, its oceans, its mountains, and every living organism inherited material from generations of long-dead stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the phosphorus in your DNA, and the iron circulating through your bloodstream all originated in stellar interiors before being scattered across the galaxy by ancient explosions that occurred long before the sun first began to shine. For much of history, the question of how the universe began belonged almost entirely to philosophy and religion. The night sky inspired countless stories, each culture offering its own explanation for the origin of everything that exists. Some imagined the cosmos emerging from chaos, others from divine creation, while many believed the universe had always existed in an unchanging form. It was only within the last century that science developed the tools to investigate this question through observation, mathematics, and evidence. Rather than relying on imagination alone, astronomers began treating the universe itself as a record of its own history, searching for clues written into the motion of galaxies, the behavior of light, and the fundamental laws of physics. A turning point came when observations revealed that distant galaxies are moving away from us, and the farther a galaxy is, the faster it appears to recede. This discovery transformed our understanding of the cosmos. It suggested that space itself is expanding, carrying galaxies apart like raisins embedded in rising bread dough. If the universe is expanding today, then reversing that expansion in time leads to an astonishing conclusion. Galaxies would have been closer together in the past. Going back far enough, all matter and energy would have occupied an incredibly hot, dense state. This idea became known as the Big Bang, not as an explosion into empty space, but as the rapid expansion of space itself from an extremely compact and energetic beginning. The evidence supporting this picture grew stronger over time. Scientists predicted that if the early universe had once been unimaginably hot, a faint glow from that ancient era should still fill the cosmos today. In 1965, that prediction was confirmed with the discovery of the cosmic microwave background, a nearly uniform sea of radiation arriving from every direction in space. This ancient light has traveled for billions of years, carrying information from a time when the universe was only about 380,000 years old. Tiny variations within this radiation reveal the seeds from which galaxies and galaxy clusters eventually formed, allowing astronomers to reconstruct the early stages of cosmic evolution with remarkable precision. Although the Big Bang theory successfully explains the expansion of the universe, the abundance of light elements, and the existence of the cosmic microwave background, it does not answer every question. One of the deepest mysteries concerns the nature of the beginning itself. When we mathematically trace the expansion backward, our current theories eventually reach conditions so extreme that they cease to provide reliable answers. At unimaginably high temperatures and densities, the laws of general relativity and quantum mechanics must both apply, yet these two pillars of modern physics remain fundamentally incompatible under such conditions. This limitation suggests that our understanding of the earliest moments is incomplete rather than finished. Because of these unanswered questions, physicists have proposed a variety of ideas that extend beyond the traditional picture of the Big Bang. Some models suggest that our universe emerged from a prior cosmic state instead of absolute nothingness. Others propose that space and time undergo endless cycles of expansion and contraction, with each new universe arising from the remnants of an earlier one. There are also theories in which our observable universe is just one region within a much larger multiverse, where countless universes may exist with different physical properties. Another possibility is that the concept of before the Big Bang is itself meaningless, because time, as we understand it, may have originated with the earliest phase of cosmic expansion, making the search for an earlier moment fundamentally different from every ordinary experience of cause and effect. One of the most remarkable features of science is that it does not regard knowledge as a finished collection of answers. Instead, it treats every discovery as an invitation to ask deeper and more refined questions. Unlike many human endeavors that seek certainty as a final destination, science thrives on curiosity. Every time we solve one mystery, we uncover another waiting just beyond it. The history of our understanding of the universe is not a straight path toward complete knowledge, but an expanding horizon where each breakthrough reveals an even greater landscape of the unknown. Centuries ago, people believed Earth stood motionless at the center of the cosmos. It seemed obvious because everything in the sky appeared to revolve around us. Then careful observations and mathematical reasoning overturned that belief, revealing that Earth orbits the Sun. For a time, it seemed as though we had finally discovered our true place in the universe. Yet that answer led to another question. If the Sun is central to our planetary system, is it also central to the galaxy? The answer was no. Our Sun turned out to be one ordinary star orbiting the center of the Milky Way. That realization prompted an even larger question. Was the Milky Way the entire universe? Once again, the answer was no. Astronomers discovered that our galaxy is only one among hundreds of billions scattered across the observable cosmos. Each discovery transformed what had once seemed complete into something much larger. When Isaac Newton explained gravity, it appeared that the fundamental workings of the universe had finally been understood. More than 2 centuries later, Albert Einstein demonstrated that gravity was not simply a force acting across space, but a consequence of the curvature of space-time itself. Einstein's theory answered questions that Newton's equations could not, yet it introduced entirely new mysteries about black holes, the expansion of the universe, and the nature of space and time. Later came quantum mechanics, revealing that the microscopic world behaves according to principles that often defy everyday intuition. Instead of replacing earlier knowledge entirely, each new framework expanded the boundaries of understanding while exposing deeper puzzles. Modern astronomy continues this tradition. We have mapped galaxies across immense distances, detected planets orbiting distant stars, and measured the afterglow of the early universe with extraordinary precision. Yet these achievements have revealed that most of the cosmos remains mysterious. Ordinary matter, the material composing stars, planets, and living beings, accounts for only a small fraction of the universe. The rest appears to consist of dark matter, an invisible substance detected only through its gravitational influence, and dark energy, an even more mysterious phenomenon driving the accelerated expansion of the universe. Together, these unknown components dominate the cosmos, meaning that despite centuries of scientific progress, we still do not fully understand what most of the universe is made of. This pattern is not a sign of failure, but a reflection of how scientific exploration advances. Better telescopes reveal fainter galaxies, which raise new questions about the earliest stars. More powerful particle accelerators uncover previously unknown phenomena, prompting fresh theories about the building blocks of matter. Improved measurements sharpen our understanding while simultaneously exposing tiny inconsistencies that may point toward entirely new physics. Every instrument extends our vision, every equation refines our understanding, and every unexpected observation reminds us that nature is often more imaginative than our assumptions, continually presenting mysteries that challenge existing ideas and inspire generations of scientists to look beyond the limits of current knowledge. One of the greatest misconceptions about the universe is the belief that its story has already been written and that science has simply been reading the final chapters. In reality, the universe is not a completed book resting on a shelf. It is an unfolding narrative, one that continues to evolve with every passing second. Stars are still being born within vast clouds of gas and dust. Galaxies continue to collide and merge, reshaping the architecture of the cosmos over billions of years. Black holes grow by consuming matter, planets continue to form around young stars, and the expansion of the universe steadily carries distant galaxies farther apart. The processes that shaped the cosmos in the distant past have not ceased. They continue to transform the universe even now, whether or not we are present to witness them. At the same time, humanity's understanding of this cosmic story is also unfolding. Every generation inherits the discoveries of those who came before while adding new chapters through observation, experimentation, and imagination. A century ago, we did not know that the universe was expanding. We had not detected planets orbiting other stars, photographed the shadow of a black hole, or measured gravitational waves produced by colliding black holes billions of light years away. Each achievement seemed impossible until advances in technology and human ingenuity made it possible. The boundaries of knowledge that once appeared fixed have repeatedly shifted outward, revealing realities that earlier generations could scarcely have imagined. Modern observatories now peer deeper into space than ever before, allowing astronomers to observe galaxies whose light began its journey only a few 100 million years after the Big Bang. Because light travels at a finite speed, looking farther into space is equivalent to looking farther back in time. Every distant galaxy acts as a historical record, preserving information about an earlier era of cosmic evolution. By studying these ancient structures, scientists reconstruct the sequence of events that transformed a young universe filled with simple gases into one populated by stars, planets, and the chemical ingredients necessary for life. Each new observation fills another gap in the story while uncovering fresh mysteries that demand explanation. Yet many of the universe's greatest secrets remain hidden. We still do not know the true nature of dark matter, despite overwhelming evidence that it shapes the formation and motion of galaxies. Dark energy, responsible for the accelerating expansion of the universe, remains one of the deepest mysteries in modern physics. We do not know whether intelligent life exists elsewhere among the hundreds of billions of galaxies, nor do we fully understand what occurs inside black holes or how gravity behaves at the smallest quantum scales. These unanswered questions are not isolated details, but fundamental pieces of the cosmic narrative that scientists continue to investigate with increasingly sophisticated instruments and theories. Perhaps the most inspiring aspect of this unfinished story is that future discoveries may transform our understanding as profoundly as past revolutions transformed those who came before us. Just as earlier generations could not have predicted galaxies beyond the Milky Way, the existence of exoplanets, or the detection of gravitational waves, we cannot confidently foresee the discoveries awaiting future scientists. Somewhere beyond the reach of today's telescopes, hidden within the mathematics of unexplored theories, or encoded in signals yet to be detected, the next great insight is waiting to reshape our picture of reality, reminding us that the universe is not only older than we once imagined, but also far richer, deeper, and more astonishing than our present understanding has yet revealed.